Welcome everyone. So it is my pleasure to introduce today's speaker, Professor Bhal Chandra Joshi. So many of us know about him. He was at NCRA for a long time. He was one of the discovery team of the double pulsar and many other exotic pulsar discovery, and he had lots of work on pulsar glitches and single pulse study, and he's one of the person who got the idea of NPTA, and he was chair for NPTA for a long time. So means he is the most energetic person, and people say youngest person in the NPTA. So we will hear today about the story of NPTA. So BCJ, please.
I have prepared this in a slightly incoherent way, so please pardon me if I sound incoherent, which I will throughout the thing. But since most of us here are from NPTA only, I will skip the part which is NPTA, the real NPTA part. Okay. Instead, I would, and also you have been hearing lots of talks in the last 3 or 4 days. Some of them very, very excellent talks, very well organized by our host Manjari here. And thanks Manjari for your kind words. So she's been very good host, and all her postdocs and students have taken very good care of us. So you have heard quite a lot, so I will not go into the technical nitty-gritties of the PTA. So here my aim is a little bit more to make it in a historic perspective, how we sort of moved into the regime of the experiment as we see today. We have no, how do I change the slide? I just do this. No, I can do from here, no problem. Okay. Yeah, no, that's okay. It's anyway, as I said, I'll informally sort of put it there. Okay, so before the NPTA started, there was a phase of germination, pre-NPTA days, and I thought that I will start with that history because much of that history is very, very relevant. The idea of pulsar timing array was not very recent as far as we are concerned, although it took us almost 2 decades to bring it to a level where we can actually start participating in a scientifically meaningful way. But the idea has germinated long back. So I would first start with this germination phase, which is how the thinking started almost now 3 decades back. So when you talk about this history, I think the first thing which one would like to do is to pay tribute to the doyen of radio astronomy in India, which is Professor Govind Saroo. Okay. He is the person who sort of initiated radio astronomy as a discipline in India and is responsible for all the instruments which we see in India as of today. And his journey in 1960s as part of a TIFR faculty member from Kalyan, which is a small town near Mumbai, in 1960s to UT radio telescopes towards the end of 60s and in 1970, and GMRT in 1990s and continuing so far. So these are the 3 major instruments which he built, and it's not just the instrument, instrument is one thing, building, but if you build world-class big instruments, you also need people who should be able to exploit these instruments scientifically in a meaningful way. So I think more than the instruments, the greater contribution of Govind has been in terms of building the radio astronomy community, which was non-existent, And we should also remember that radio astronomy as a discipline matured only in 1950s, just around the time when Govind from Australia had moved to US to work with Bracewell on the VLA thing. In fact, the early VLA design, a lot of work was done by Govind. So I would actually not go into that history. I would how do I go back? Yeah, I would sort of stick to more recent history, which is post 60 and so on and so forth. So after the Kalyan radio telescope, which was basically a bought out instrument, he got the dishes from somewhere else and put them up to make a solar interferometer. Govind's first big venture was Udagman radio telescope, which is also known as UT radio telescope or ORT. And this was a fantastic instrument because it was an equatorial telescope. Radio telescopes are normally altitude and azimuth mount. This was an equatorial telescope, just like an optical telescope, with a 1024 steered phased array. So it had a phenomenal collecting area of the order of 7,000 square meter, which was much larger than the Jodrell Bank dish and the Parkes dish at that time. So the two big telescopes which existed at that point of time, this was not only equivalent to in collecting area to those telescopes, but bigger than that, and a completely revolutionary design in which the equatorial mount was by virtue of a natural slope of 11 degrees in Ooty. So he and Homi Jahangir Bhabha, who founded TIFR, they went and found a hill which had an 11.5 degree slope and located this fantastic telescope on that, and that made it equatorial mount. So, and it also reduced the cost. The telescope itself was built at 1/20th of the cost of a similar collecting area anywhere in the world, and Swaroop was famously known to sort of put this out in an equation which is well known as Swaroop equation for building the lowest cost telescopes in the world, and he did the same thing with GMRT also. The other important thing to note is this telescope started operating, the first light was in 69, which was just 2 years after the discovery of the first pulsar. So the hope was that this will make great deal contribution as far as pulsar astronomy was concerned. It was just in time for pulsars. But alas, that didn't happen because in 71 the Ooty radio telescope had a massive accident, okay, somewhat like the GBT's 40 foot, and it all collapsed completely. And that was a big setback in the early days for radio astronomy, and that also meant that the period between 70 to 76, when most of the really phenomenal pulsar discoveries took place, Ooty was out of action. Okay, it really didn't come up to the level where it could contribute to pulsar astronomy. The other aspect was we were very new. India was typically 30 to 40 years behind Europe and US and Australia, which meant we did not have atomic clocks, which meant that we did not have fast chart recorders. Computers were not there in those days, but you used to do everything on chart recorders. But for pulsars, since the periods were of the order of second, you needed fast chart recorders. And there was no company in India which manufactured this. Importing them from Europe or US was almost no-no because it was terribly costly given the exchange rate this thing. So that was another limitation because of which doing pulsar astronomy was not really something which fitted the bill as far as Ooty is concerned. So Govind actually moved to lunar occultation and cosmology, and Ooty's largest contributions have been in those fields and not in pulsar radio astronomy. Nevertheless, Ooty did several pieces of pulsar work which did not require the kind of precision which we are talking about, and I have just listed a melange of papers by Krishna Mohan, by Balasubramaniam, Ramachandran and Deshpande, Dipankar Bhattacharya and others who used this telescope to produce really useful scientific pulsar science in 70s, 80s, and even now Ooty is actually producing some amount of data with respect to that. But the early advantage which you get when a field opens up, and we were very well placed for doing that, got lost. And that had been the greatest regret of Govind Swaroop. Many a times when we have sat together and chatted, one thing which he told me is that this is something which he regretted all his life, that he could not really do something on pulsar astronomy. And those of you who have not met him or are not aware of him, pulsar astronomy was much more closer to his heart than other fields. Okay, and he would have liked it to develop to a larger extent, but it didn't happen as far as the Ooty radio telescope is concerned. So, yep.
You said it was ready in 69, right?
Yes.
So between 69 to 71, no pulsar work was done?
No pulsar work because of the other reasons, like you needed a chart recorder. Okay. So even today in India, if you want to buy things, it takes you 3 to 4 months. That was a time when to get a thing from abroad would typically be 2 to 3 years kind of thing. So he just got some of the things. One of the first I think fast chart recorders came around the time the telescope collapsed. But then the telescope was gone, and In India, where the money for science is very small, okay, you take some money and build a big telescope and it collapses, that usually means the end of the career of that scientist, okay, which of course didn't happen for Govind because he was very resilient, okay. He did not get disappointed by that. You can imagine, it's not just Govind. There were 4 students, Vijay Kapahi, Anand Krishnan and so on, who actually built this instrument by their own hand. There was no contractor, there was no laborers to actually make the electronics. Everything was done by the students, 4 of them. And their PhD thesis depended on this instrument, and the instrument collapsed. So this is a good example for today's students, okay, where you get data easily from wherever it is, okay, you don't really bother about it. But imagine that your PhD thesis is dependent on a data from an instrument which you have built with your own hand, working day and night for 2 years, and the instrument collapses. That's the end of your career, okay. But all of them, of course, went on to do great things. So Anant went on to do solar physics to a large extent. Vijay Kapahi became a big name as far as cosmology is concerned. But the bottom line is that the group was at a lowest point in 1971 within TIFR. Of course, the support from the TIFR was also quite large, and because of that we came up again. But one should just remember that all things don't go hunky-dory. You have to go through various hoops before you actually reach somewhere. So he was not unfazed by that accident, and he went on to first propose what is known as UT synthesis radio telescope, where he wanted to have several UT-like telescopes which will do interferometry. Okay. That also did not really take off, and then he came up with the first idea of SKA. So way back in 1980, Govind was talking about square kilometer array, and that time he was calling it as giant equatorial radio telescope, where on the equatorial belt of the earth in Africa, in US, in India, he was trying to make a set of telescopes which will work like an SKA. But of course, again, that idea also did not take place. But he continued with his ideas, and finally out of that came GMRT, which also was very innovative. And his regret about pulsars not being the mainstream science for UT meant that here he put in a lot of effort and thought in designing this instrument such that pulsars are an important part of GMRT. And today, pulsar astronomy is a very, very vibrant part as far as GMRT is concerned. Okay. So this is just a picture from the early days, 1992. The first time I saw an antenna was in 1992, when just even this top part was not there, just the tower was there, and 93 the first antenna was commissioned. Okay. So in the middle is the main mechanical person who is no more with us now, Bhaskaran, who actually tirelessly worked on all those. And you see, if you look at GMRT today versus what it used to look at that point of time, you can't even imagine that this whole thing would have become something like this.
Who's the other person?
Who was the other person? Yeah, no, it's not me. Okay, I had lost my hairs by then. So this, I don't remember who it is. This is Bhaskaran. Of course, this you know is Govind. Okay.
That one behind some instrument.
This?
No, not the GMRT.
Down, yeah, the red.
These things?
No, that corner.
There's some.
This?
Yeah.
This is a dish. This is basically the hub of the dish. So the thing which comes here, it was always constructed like this and then lifted back in that fashion. Okay.
So they have huge cranes to do all this?
No. So this was low cost. Okay. So this was all built by locally made material, by local contractors who had zero experience of this. In fact, one of the contractor, VM Zog, he only used to build bridges. Okay, he had no idea of building telescopes. So he learnt along with us, and both the contractors went into loss because there's no profit to be made out of this. Of course, they used the fame and name which they got for building GMRT in other projects, but from this project they did not get any money. Okay. So they both sort of lost a huge amount. In fact, one of those companies was from Chennai, Southern Structurals Limited, and that company has gone bankrupt. Okay. So So yeah, this is not new. I was hearing a talk by Sir Bernard Lowell in Jodrell, and in fact he himself, Lowell, and his contractor, husband or co or something, I don't remember, they both had almost become bankrupt if the Sputnik was not launched. So because of Sputnik. So most radio astronomy stories are like that. Anyway, so while the GMRT was coming up, pulsar astronomy was still developing, and Rad Radhakrishnan had returned back from Australia, and he had started a very vibrant group at Raman Research Institute, and we have Prabhu here from those days also. Okay, Rad was still alive at that point of time. And all these people, because there was no instrument, so they were focusing on world-class theoretical research. Okay, so a lot of theory was being done at RRI at those days. On the other hand, Govind wanted to have an observational astronomy group at NCRA, or that time it was still called as the Giant Meter Wave Radio Telescope Project. So he started collecting people who could actually form the nucleus of a pulsar group. And this was a very unique partnership with RRI. So Rad and Govind, they sat together and they decided that Giant Meter Wave Radio Telescope will not just be a TIFR project, it will be a TIFR Raman Research Institute joint partnership. And I think amongst the instruments which we have in India, it is one of a unique initiative which GMRT is. No other, you don't find that kind of a collection of people coming together. Both were very strong personalities, right? But it didn't come in their way of getting together and doing things. And Prabhu can tell you better than me that there was no restrictions between the two institutions. These guys used to land up at middle of night in Pune, don't even come to NCRA, they would straight go to GMRT. Okay, so, and nobody would stop them. So it was a very beautiful environment to work in, and because of that unique partnership, a lot of hardware was developed at RRI for pulsar work and installed at GMRT. At the same time, we focused on GMRT feeds and things like that. And with Dipankar and Desh working together, some of the unique capabilities of GMRT was designed by Govind into the instrument, and these are the ones which we use for NPTA experiment today. Okay, so why I am stressing this point here is that the whatever fruits of these people's labor, that we are getting the kind of unique data set which we are getting. Without their thinking, we would not have got the quality of data which we are getting. And that unique capability is the subarray capability. I think at that point of time there was no instrument which had a subarray concept. Okay, so Govind right from those days in late 80s, 88, 92, 93 had thought of GMRT as a telescope in which you can divide it into 2 or 3 or 4 different subarrays, each of them having a single beam, and each of the telescope independently observing various things. And he wanted to do a wide frequency coverage out of that. Okay. So this was built into the design, that you had a subarray capability, you had a digital beam forming, and some of the state-of-art chips had gone, FPGAs and ASICs and similar digital hardware has gone into forming beams, multiple beams, and frequency coverage right from low frequency to large frequencies. And obviously the low frequency, one of the reasons for going for low frequencies was the steep spectral index of the pulsars, because this is the place he knew that pulsars would be the brightest, and we can really make a mark as far as providing the most unique data set to complementary to any telescope in the world. So when he passed away, in his obituary, many people did mention that he was told by Posse long back, he don't do science which is bandwagon science. That is, if everybody is running towards a particular topic, you don't go and join that, because that's not what is going to get you any laurels. You pick up something which will mature over a period of time, and then obviously when the field matures, you are at the right place at the right time to be able to make a unique original contribution of yours, not otherwise. Okay, so that is what he focused as far as GMRT is also concerned on. And at the same time, as I said, he was a people builder, so he recruited people who could form the pulsar group at GMRT. So Vivek, Yashwant, myself and a couple of others all of us, Sanjay Upreti and others, we all joined at that point of time to start working out a Pulsar program as far as NCRA is concerned.
Sharma ji was there, right?
Sharma ji was in Uti, went to RRI, okay.
But he was not part of NCRA.
He was never part of NCRA, but he was part of RAC. From RAC he went to RRI, and Prabhu can correct me if my chronology is correct. But he did a lot of work for GMRT.
That's what I think.
Yeah. No, so these lines were very blurred, okay. What is RRI and what is NCRA? It was Markandelu, for example. So you used to call him Mark. Markandelu was probably employed by us, but he used to work with you. I don't remember also, okay. Because he was never there in GMRT or NCRA. Most of the time he was sitting at RRI, okay. But I think his salary used to come from us. And Anish Roshi is another example, okay. Anish is at Arecibo right now. Same thing, okay. Or GBT, yes, he's at GBT. So Anish, same thing. Most of the time he was sitting in RRI. He never came to Pune, okay. So I think there was no sort of logical separation between what is RRI and what is NCRA. People used to move across very freely from one side to another side, okay. So that's the unique partnership which was there. Okay. So while we are looking at the in-PTA history, I think I will take a little detour into the world history also at that same point of time. So in that early phase, a lot of Pulsar work was done, and based on that Pulsar work is initially done by Joe Taylor, Dick Manchester, Andrew Lyne and Don Becker, okay. Lots of different areas had opened up, okay. And in particular Don Becker, who sort of was a jack of almost everything. You talk of millisecond pulsars, you talk of pulse emission mechanism, and of course you talk of Pulsar Timing Array. Don had his hand in it, and on top of that he was also a brilliant instrumentation person. There was a time in 2003-2004 where if you go to any telescope, you will find one instrument or a back end designed by Don, okay. So he had this habit of designing things and leaving at different telescopes, and all very state-of-the-art things. So these guys had actually sort of developed the things, and a little before that, the concept of the Pulsar Timing Array had started with Sazin, okay, where he had proposed that you can actually use pulsars to set some limits or some bounds on the gravitational wave from a stochastic gravitational wave background, and this idea was taken further by Duttweiler. So the theory had started developing there, and Hellings and Down and Becker and Down in late 80s and 90s worked out the basic theory of what we know today as Pulsar Timing Array. That is an ensemble of pulsars all distributed all across the sky, which would measure a very typical characteristic spatial correlation, which is known as the Hellings and Down correlation. So all that was done by Don Becker, and the name Pulsar Timing Array is also thanks to Don Becker, because he is the first person, to the best of my knowledge, again Maura can correct me, but I think to the best of my knowledge he is the person who coined the term Pulsar Timing Array. So these were the, I would say, the giants of the Pulsar Timing Array. And of course Dick started the PPTA experiment in 2002 from a federation grant, using Parkes to do the regular cadence monitoring of the pulsars, which we know today as the Pulsar Timing Array, okay. And eventually these from these gentlemen developed all of our Pulsar Timing Array community. So this was what was happening in the world the time we were building GMRT. So that time we were not doing any science, we were doing some small little pulsar things, mostly focusing on building the GMRT as an instrument. And when this was also happening, a very lucky instance happened that there was Diamond Jubilee of the Indian Academy of Science in 1994, and Professor Radhakrishnan invited the entire pulsar community to Bangalore, okay, at RRI, and there was a very beautiful, fantastic symposium. I actually learned most of my pulsars in that symposium. So that 5-day symposium sort of gave you an overview which no book can give you, no other things can give, because all of them were there. And Govind was, because he wanted pulsars to be a very important part of GMRT, he immediately booked tickets for all of them to Pune. And he said, you all have to come to GMRT and see that. And what you see here is some of them. There is Dick there is Vanden Heuvel here, and Andrew Lyne here, and of course Govind here. I don't know who he is, okay, I've forgotten who he is. Maybe Blandford. They are all young, so as you can see, Andrew looks so young now. So I don't know who he was, but all of them were there. And we had a fantastic dinner, and during the day there were lots of discussions. And the idea of pulsar timing array using Indian instruments or using GMRT was first proposed in 1994. Okay, so historically, if you look at it, this idea came way back in 1994. So we are what? We are 28 years into the history. Okay. Of course, this was the time when Don himself was trying his level best to get PTAs going everywhere. So he was going everywhere and talking to people and trying to convince them that you can actually detect gravitation. Remember, this is much before LIGO detection, right? And the LIGO experiment and other gravitational wave experiments had been working for decades without any detection.
LIGO just got approved.
But there were other precursor experiments which had been working with almost negative results. So when Don was speaking about PTA as a gravitational wave experiment, nobody would be convinced. Okay, so his only hope was to go and talk to everybody and convince them that this is a good science experiment. Okay, so he did the same thing here, and he told Govind that if you want to really make a mark as far as pulsar science is concerned, this is the experiment. Okay, and remember, this was not bandwagon that time. PTAs were not known. Okay. And Govind, with his penchant for picking up topics which will mature not today but 20 years down the line, he was immediately attracted to this particular idea. And so oops, how do I go? Okay, so the very next day after these gentlemen had disappeared, okay, he called Vivek and myself, and we had a 3-hour grueling session. With Govind, every session was a grueling session, because you would come and it will become 1:30, 2 o'clock. His wife Beena will call some 10 times, ki, please come, there is lunch time. Then she will also call us and say, ki, tell Govind ki it's lunch time, but he would not go. Okay. So, but you also had to sit through. Okay, so we were told ki, you should have timing capability here, because without timing capability, we will not be able to do this particular experiment. And these are the words actually told by Don Becker to Govind, that the best way to explain a gravitational wave detection by a pulsar timing array is that you have pulsars spread all over the galaxy, and they are bobbing up and down in the space-time. Okay, so if you can measure this bobbing up and down of the pulsars, you will detect gravitational waves. And Govind sort of got it exactly right on the task. He told us exactly in the same words, you see, this is such an exciting experiment. Okay, Vivek, my supervisor, was very conservative person, so he immediately said, Govind, right now even the telescope is not phasing. How can we do timing? First thing is to see pulses, then we can time them. So it is out of question. Okay, but nevertheless, I was joined with 2 more students, Ravi Swain and Mohit Sinha, and the 3 of us were formed a team to sort of evaluate how to get timing going in this thing. And the first thing I discovered was that Vivek was right. We had a clock which used to jump, which used to drift everywhere, and nobody understood how stable a clock you should have had. And if you needed to get a TOA to the kind of precision which we are talking, that was simply impossible in 96, 97 and so on. And plus, we had no experience with timing. Nobody here knew what is tempo, nobody here knew how to get a TOA and so on and so forth. So the first task was for us to do a template matching, and Mohit and myself spent quite some time writing a program to cross-correlate a profile with there was no profile because data was not coming, the telescope was not ready. So we simulated a pulsar and we simulated another pulsar and we tried to get the TOA and study. Mohit's project was exactly this kind of a thing. But TOS we finally got. However, we did not know how to use tempo. So although Joe Taylor was probably one of the first astronomers to put in public domain the software which he used, nowadays you guys go to GitLab and just download, right? Left, right and center. In those days, the Pulsar software was not available. And Joe Taylor was, I think, the first astronomer in such who actually put it in public domain. So he put the full source code. So I could download that. But there was zero documentation. Okay. So you had absolutely no idea what is a TIM file. Okay. So the only way was to reverse engineer. So 96 to 98, 2 years I went through the entire source code to try to figure out how to make a TOA file. Forget about TIM file. Forget about actually getting a timing solution. And finally in 98 we were able to time 0329 plus 54. And the timing which we were able to do was not stable. So you will get good residuals, then a jump, then good residuals, then a jump, then a good residuals and then a jump, and we had no foggy idea why this is happening. Okay. By hindsight I know that the clock was horrible and we were using a completely useless clock, but that time we did not know that you need a very ultra stable clock for doing these kind of things. Anyway, then I went the best way, and Richard Welebinski was visiting us at some point of time, and we were sitting on the dining table and discussing various things, and we were bad mouthing the whole Pulsar community because nobody shared what they are doing, okay, or how timing. I wrote actually to many people and there was zero response about how to do timing and what are the things. I wrote to Dick also, I think I remember at that point of time. There was zero response from Dick. Okay. So what to do, and I told Richard Welebinski this is the problem. So Welebinski said, oh, you are not unique. I have a 100-meter dish in Effelsberg and my group also does not know how to do timing. So I had to send Michael Kramer all the way to Jodrell so that he can sit with Andrew Line and learn how to do timing and come back. Okay. So I realized that sitting in India this is not going to happen. If we have to learn, we have to go outside only. And that is what then we started doing. Okay. So Vivek, Yashwant and myself, we all sort of moved out to try and learn, because by the time the instrument was finished. So 1998 GMRT was fully commissioned. So all 30 dishes were up. The electronics was ready. And by 1999, around the time Ramesh Bhatt left this place, we had finally got the beamformer working and getting a phased array output where we were getting somewhat like n times improvement when you add n number of dishes. Okay. So we knew that we are now in a place where we can actually start attacking these scientific questions. But what to attack? So there were two possibilities. One was to do exactly what the UTI guys did, what Dipankar did, Desh did and others did, which was to focus on the interstellar medium. So throughout the 90s, UTI was actually doing pulsar observations, but they didn't have timing, they didn't have all those things. So what they did was they looked at bright pulsars and used pulsars as a probe of the interstellar medium. So basically 325 you can do good scintillation studies. So they did scintillation studies or scatter broadening studies, and I think Ramach has a paper which I showed earlier on the scatter broadening measurements from UTI and so on. Dipanjan also at that point of time sort of joined into the entire thing. So we had one option to just do that. Okay. That was the easiest because it was continuation of our strength in the field, and just take it to GMRT. But Govind wanted to do timing. Okay. And that meant that this conventional thing cannot be done, and we had to go and learn some things. So my time at Jodrell was very useful because I got involved in the Parkes multi-beam survey, and that's where I first met Mora also. Okay, we were part of the same survey and so on. And in the process, I learned that we need to have at least a maser at our observatory or something which is comparatively stable like a maser. Without that, thinking of doing timing is completely useless. Okay, we should at least have a GPS, if not maser. Okay. 1999 GPS were not made in India, and even in 2003 GPS was there, but there was a mode called select availability mode or SA mode, which meant that the timing precision of GPS anywhere outside US was degraded significantly. So you couldn't use GPS also for doing a high precision timing. So you needed GPS plus a good clock. This is what I learned. And so after coming back, the first thing which we started, Yashwant and myself, was to try and convince people in TIFR that we need to buy this, okay. And it's only around 2004 or 5 when we actually discovered pulsars with GMRT that our case became strong enough to convince our people in Bombay that we really need money to buy these kind of machines. And as luck would have it, Professor Sen Gupta, who retired as director of NPL later on, he was developing locally made GPSs and also developing a maser. Okay. So he also got interested, and between this small group we actually got a clock installed in 2004, and I spent 2 years characterizing that clock because we needed to get exactly the LN variance of the clock and make sure that everything is fine to be able to do that. The Indian GPS, which was cheaper, which we purchased, had again jumps. So we had to talk to the manufacturer and get that fixed and so on. At the same time, we did start other pulsar signs, and the first pulsar survey which we started at GMRT, of course, Mora came here to do the first observations. Okay, so I think yours was the first pulsar survey observation with the GMRT, as far as I remember. So we did that survey and we discovered some pulsars there. And by around 2008, we had a reasonable timing of millisecond pulsars going. And then again, as luck would have it, I was going to Montreal for some conference. So I decided to stop in over at GBT. Mora invited me kindly there. And it so happened that Joris, which some of you will know, okay, he had, I think, finished his thesis, or I don't know. He was visiting as a postdoc or something like that. Yeah, so he came there and he gave a talk, and in the talk he mentioned dispersion measures, and Dunk immediately suggested to me, hey, you guys can do a great work, okay. So I remember a discussion in the afternoon somewhere in GBT at that point of time where Dunk suggested, you guys, why don't you go back and convince your people to do multi-frequency observations to get DM estimates, okay. So technically speaking, our experiment began in 2008 in some sense, okay. It took another 6 years before we reached where we reached, but the basic ideas actually started historically in 2008 from that. So after coming back, Rajaram was the director, and Yashwant and myself, the three of us, we sat together, and I tried to convince Rajaram that we need to have some guaranteed time, so that we can do, because Dunk had made a point that we need a very good cadence. So if you can do a DM measurement once every week and combine it with nanograv or PPTA, you will make a big difference as far as this is concerned. And I thought that it was an extremely valid point. So I tried to convince people ki give us time, you know, exactly what they need. Give us guaranteed time. We can't go through GTAC for this because the time allocation committees, it's a potluck. But Rajaram said, see, that is not possible. This is a competitive time, so you have to apply like everybody else and come. So in the end, Yashwant and myself, we decided, okay, we will do that. And Yashwant put a student, Ujjwal Kumar, in doing all this. And I think Ujjwal did demonstrate in principle that you can measure DM variations. Okay. That experiment was slightly different from what we do. Now we divide the telescope into two telescopes, one at band 5, one at band 3, and do simultaneous measurements. And our simultaneity is on timestamps. Because our clock is very good now, we have a maser and everything. Okay, that time we didn't have maser. Our GPS also was a bit wonky. So obviously we couldn't have done this. So in 2001, 2002, when we were discussing what kind of science we can do, Yashwant came up with the idea ki why not divide 32 megahertz into two chunks, 16 and 16. Put one frequency in the upper half of the band and one frequency in the lower half of the band. Then you don't need a timestamp because the data is coming simultaneously. Okay, and we can measure DM. So that is what Ujjwal did in 2009 to 2012, and I think he has a paper somewhere. Yeah. So this was a feasibility experiment, and so he sort of monitored about 11 pulsars using this technique. So which means that both the telescopes, there was only one beam, not two beams, only one beam, but the upper half of the beam was one band and the lower half of the beam was the other band. And with that he was able to show that, and in this I think we selected 4 pulsars which go very near the sun, 2145 being one of them. And he was able to show that there is a small increase in DM when the solar elongation is very, very small. This is just after the other paper which came from Parkes showing that solar wind is important. So this was sort of a precursor experiment, and this gave us confidence that we should be able to do something on the DM. But unfortunately, since we were going through TAC, so sometimes you got time, sometimes you didn't get time, and the time was not sufficient to do weekly cadence. It was sometimes 2 months, sometimes 1 month, so it was all very erratic experiment and didn't really qualify as a proper experiment as far as this is concerned. And then soon after Ujjwal left, so this project sort of came to a total standstill. Okay, so it sort of failed in some sense, so to say. So this was the prehistory, the germination phase. So this was the phase in which the ideas were just coming, and some idea here, some idea there was clicking, but there was no concerted effort to make a PTA. So that was also the time when Gopu was hanging around in NCRA, okay, and he is doing his GMU news and saying ki, I can prove X wrong, I can prove Y wrong, I can prove Z wrong, okay. So can you find some data to prove this wrong, okay. So I thought that instead of proving different people wrong, if we can prove ourselves right, that would be better. So I tried to sort of slowly cajole him into a direction where we could bring up a community. And one thing which I learned in the early days was, you can make a fantastic instrument, but if there are no people to use it, that instrument is useless. Okay, and in the first few days of GMRT, the one reason why we did not make much progress was there was 0 students. Okay, so between 2000 to 2010, total of 4 students in NCRA came and made use of GMRT. Outside NCRA, there were only 3 to 4 students. So 8 PhD students in a span of 10 years with an instrument like this. Okay, and the net result is that the scientific contribution in the first decade of GMRT was very, very small. Now, partly it was because radio astronomy is not very fashionable, or was not fashionable even in those days. Most physics students in India would go for condensed matter physics. They would not even come for astrophysics. Okay, so it was very clear to us that if we want to have a good manpower built here, we will have to go and do an outreach. And another thing which I saw during the GBT thing which impressed me very much was the Pulsar Science Collaboratory which Mora had started. Okay, you could see high school students coming and getting excited in doing pulsar search and so on. So I said, what the heck, who says radio astronomy is not exciting? Okay, it's we who are not delivering the message in the right format to make it not so exciting to the students. So that is where the winter school was started, and fortunately we got money. So that is the first time we got a big chunk of money. So we thought that instead of going for hi-fi experiments, let's go to the students, because let's build the community first. And then Gopu suggested we should have a Pulsar school, and that is where the Pulsar Observing for Students school came up in 2012 at Ooty. And some of you have, Manjari has certainly, and so on, have actually taught in that school. Now, for doing that school, we needed to get Ooty working back as a pulsar instrument, and in between, from 2000 to 2010, Ooty had stopped doing pulsar astronomy. So, with one of my students, we started building a backend there, and a new digital backend for doing coherent de-dispersion was sort of designed at around 2011, and Arun Naidu sort of built this. The legacy data which we were discussing in the morning, all that data has come from this backend called Ponder. Okay, so he built this backend there, and we use this backend first for doing simple things, simple bright pulsar observations, which students can themselves do, and train students in getting them the excitement of the pulsar astronomy. And I think that was a very useful experience, because we got lots of people excited. And to some extent, I think all those people who came in 2018 had some connect or other with the PAUSE program and so on. Okay. Unfortunately, funding ran out, so we stopped that PAUSE program. Today, there is no Pulsar Observatory student program in India, but that program had a very important role to play in. So, although it's completely unrelated to NPTA, but in some very strange way, I think that had a very big contribution in getting the NPTA up. If nothing else, in getting me and Gopu arguing with each other, going to Ooty every 3 months or every 5, I don't remember, okay. So many times we have gone there. So then once this experiment came, then we started, I thought that instead of GMRT where you don't get time, you have to go for every damn thing, you have to go to time allocation committee. Ooty is much better because it's under our control. So let's do a proper high cadence experiment here. And I think that's around the time when I wrote to Mora also, and I wrote to Dick. Dick came for a conference in 2012 to RRI, Astronaut Conference on gravitational wave. And Bala had invited me for a talk on Pulsar Timing Array, and Dick was giving a talk on survey. So at the end of that, we were anyway supposed to write an article. So I discussed with Dick, and Dick said ki if you can use Ooty for a daily cadence, that can make a difference. So although it's not a big instrument, it's not so well sort of into the PTA program, but a daily cadence will still be useful. And this is around the time when Harvey Siemens had written his paper on the scaling relations, in which cadence played a very, very important role. So immediately both of us decided ki we should try and push this angle. But then we got stuck again with the clock problem. And so Mayuresh spent quite a lot of time trying to, Mayuresh and Krishna Kumar, they spent, both of them most of you know Mayuresh and Krishna Kumar. So they spent a lot of time trying to understand why this is coming. And eventually we fixed this problem. As you can see, from here onwards, everything is very, very, very smooth. Okay. So morning you were asking when can we have an overlap with WSRT? Okay. We can, frankly speaking, have an overlap only from here, which is 57,500. Now I don't know which year it is, 57,500. Probably it is 2016. So if it is 2016, then we will have very little overlap with WSRT. But if it is before 2016, maybe some 4 or 5 months we might get. That's it. Okay. So this was fixed, and this also meant that we had to look at the GMRT clock. So from 2014 onwards, once Ponder was commissioned, it became a cycle, we do something at Ooty and then take that experience back to GMRT and fix the same problem at GMRT. So with this cyclical closing of the loop, we were slowly able to improve the performance of the GMRT also. Of course, as this happened, we thought ki now is the time for proposing a pilot experiment. So in 2015, we proposed a pilot experiment. Again, time allocation was a problem, so it was very clear that we will not get more than 30-40 hours, okay, because who will give, this was pre-gravitational wave discovery thing. So I was 100% sure that TAC will simply refuse, they will not give any time. So I said, okay, let's start with 40. So Manjari had also joined us by that time. So the three of us, we decided, ki, okay, we will go for a very modest time. We will go for a very small sample, 9 pulsars only, and we will rely on Ooty fully. GMRT we will do once a month cadence. So the requirement of GMRT time is very small. Nevertheless, this will allow us to build good solutions of our own, because Ooty we had a daily cadence, which means that we can get very nice phase connected solutions as far as all these millisecond pulsars are concerned. So this is that phase of the experiment, which is also the legacy data which we discussed in the morning, and some of the early results were very, very encouraging. So at some point of time Yashwant got interested, and since the upgrade of GMRT was taking place where we were getting wideband receivers, so Yashwant said ki, okay, we need to test those receivers for precision timing. What better thing to do but to start something like a PTA experiment for the upgraded system. So these early results are from the legacy GMRT and Ooty, so not the upgraded GMRT, that is GMRT with 32 megahertz bandwidth and 4 discrete bands. But since the upgraded system had become available in 2015 but was not released for, so the other helpful thing there was that this was an experimental system, not available to time allocation, but with some internal availability of test time. So he said, why not put an experiment on this, and we did. Initial results were good, so then we went to, there was a shared risk phase for upgraded thing. We continued with that proposal, and eventually sort of that is the proposal which, okay, so this is also the early DM estimates from this. So that is the proposal which became the full INPTA. Okay, so that is 2016, late 2016 and so on. Okay, so all that data you have analyzed in DR. Okay, so this is now I have come to the place where our DR1 starts. Okay, so this was all the history before that. DR1 I call as flowering and maturing of the INPTA, because from this point onwards we knew exactly what we are doing. And we had Krishna Kumar, Mayuresh, we had few more other people who were now trained in doing timing. Okay, so it's not just that I have to sit or Manjari has to sit and do all the timing, or Yashwant has to sit and do timing, but there are other students whom we had trained and taught how to do timing. So we were confident that if we have, like what Shantanu keeps saying now, who is going to do observing, who is going to do data reduction? Okay, that was a problem. So we had now some people to do this. So we started doing on a regular basis. Okay, I will skip all this because in fact most of things now onwards you can happily ignore, because that was meant for general audience, not for INPTA people. So and anyway, you have heard in the last this thing, Maura actually gave an excellent talk on this, so I will quickly move from this to the important aspect. So in the early days also it was clear to us that it's the low frequency which is going to make a big difference, but neither Yashwant nor me nor Gopu were very sure how much impact it will make. Okay, so yes, we will get DM variation, but how does it really make a difference, and whether band 5 TOAs will be reasonable enough or not. Okay, so the important aspect which became highlighted at that point of time was that one of the biggest challenges, and Jim Cordes told this to me in some meeting, I think 2017 meeting or somewhere, that you have only two pulsars really, frankly speaking, which can do PTA work. One of them is now controversial pulsar 1713, but 1909 was the other pulsars. So he said all other pulsars have all kind of noises, and it's not sure that you could ever get gravitational wave background out of that unless you characterize every part of the noise. Okay, and that was the time when Steve and others were actually writing the Bayesian codes to do the noise analysis and so on. So all this was very open at that point of time. So one of the source would have been the dispersion measure kind of thing, and Dick had just published the PPTA results, the first PPTA results, and I could see that some of the pulsars have such a large DM variation that even if we are not very high precision, even if we are second or third decimal place precision, we should be able to characterize them. Okay, so theoretically we should be able to go 1 part in 5 or 1 part in 6, but practically at that point of time I didn't believe we will ever be able to reach one part in 5. Okay, now it looks a little weird now that we have done that, but that time I thought was probably not possible. But nevertheless we will be able to give DM variations which would be useful for any IPTA kind of effort. So the important aspect was that propagation effects such as dispersion and scattering needed to be characterized in one way or another. So GMRT could have a unique niche role in the IPTA experiment, because we could provide that low frequency end of the PTA which was missing. So of course rest is history, in the sense that we became associate member. I wrote to Dick, and then Dick sent me to Dunk, who was the chair I think in 2016 or 17, I don't know when he was the chair, and and I think I wrote to you also when Justin Ellis had come 2016. I think we had this ICTS conference, and I wrote to Maura saying, can we become some kind of member of IPTA, because anyway we can't do much as far as gravitational wave is concerned, but we can certainly contribute our data. So it would be good for us to become a member. And Dunk was the steering committee chair. He was gracious enough and he said, yes, please join. Okay. And although you will have no voting rights, nothing like that, but if you are happy to sit as an associate member, we are very happy to have you there. And I said, yeah, we don't want any voting right. We just want to learn from you guys, because most of our learning till this date we have done on our own, and we have wasted 20 years in learning that. If we sit with you, we might be able to do it much better. And we have now a young, vibrant group of students along with us, so it would be very good for them. So we became associate member at that point of time, and I think 2 years back we became the full member, 2020 and so on. And now there are other experiments also coming. So this is the full IPTA thing. Okay. Should I go through this? Is there anyone who is not aware of any of this history? Because huh? Yeah. Okay. No. So no, I don't want to sound boring, okay, because all this you guys have heard 1 million times from me, so I don't want to be boring, but in the interest of general audience, let me sort of go through that. Okay. So this feasibility experiment we started with UTI, and then we started the pilot. This I have already said. Okay. And since 2018 we have started using only UGMRT. So now UTI is not part of our experiment, because UTI slowly is degrading, and now it is not at a level where it can provide very high SNR data. On the other hand, UGMRT has become a very well tuned instrument, so our entire observation strategy has gone to UGMRT. And last 1.5 years back, we also had our Japanese colleagues join us. So now we are a wider collaboration, and if as I understand from Gopu, we are trying to widen the collaboration even further. So we may have slightly more people coming into the experiment. But currently we have about 40 people, which is Indo-Japanese collaboration, which primarily uses the upgraded GMRT for doing the Pulsar Timing Array experiments. Okay, and there are several students and so on and so forth. Right now we are observing actually 22 pulsars, so this has got revised further now. Okay, so we are observing 22 pulsars on a bi-weekly cadence. So that has now become a very standard practice, and the good thing which happened because of the early results is now the TAC is very supportive, and except for one cycle in which they rejected our proposal, for all other cycles we have got time. Okay, so not fully, yeah, they are still not giving us the kind of time which we would need to have, but anyway, with an instrument like GMRT it's going to be difficult. So because of that, now we have a very regular cadence and so on, and we are able to do what we set out to do, which is to characterize the slowly varying interstellar medium induced noise from the gravitational wave signal. Okay. So what is this noise? Again, now you have all heard, but I can again, in the interest of the general audience. Okay. So the pulsar signal is a pulse signal. It's not a continuous wave. So you have a delta function which is traveling towards you from the pulsar. Now the free electrons in the interstellar medium, they disperse this signal, and because the group velocity is a function of the plasma density. Okay, so because of that, the pulse arrives at progressively later times as you go down in the frequency. So that is the phenomena of dispersion, and that is what you see here. If you see this is the higher frequency, 300 megahertz. No, sorry, this is the higher frequency, 500 megahertz, and the upper frequency is 300 megahertz. Of course, in that plot, the dispersion has been mostly removed, but there is some residual dispersion, and because of that, you see the bright patches are the pulse at a given frequency. So the x-axis is the phase of the pulse, and the y-axis is the frequency. So at different frequencies, the pulse is arriving at a different point of time. So if you do not take care of this, the first simple connotation of that is that you will not see any pulse, because your pulse will get smeared out. Okay, it will be all over the phase, which means that when you add all the frequencies, you won't see any pulse at all. Okay, so you by force have to remove the dispersion, which is called the process of de-dispersion, to be able to see the pulse. But if you do not remove the dispersion accurately, then also there will be a small residual smear left in the pulse. So when you now time this pulse, that is find its time of arrival, that time of arrival will have a small error bar, and that error bar will have a contribution from the dispersion smear. Okay. So you need to correct for this. The other low frequency propagation effect happens because the pulse signal, when it starts from the star, it goes through a medium which is not homogeneous, which is inhomogeneous. So because of this electron density variation, you have multiple refractions, and the pulsar signal which started at a point on the star goes through multiple paths and again constructively and destructively interferes on your telescope. So this interference can manifest in two ways. One is that you see brightening and fading of the pulsar as a function of frequency, which is known as scintillation. And the other thing is you see the pulse getting smeared because you have different delays from different paths. So the pulse comes with slightly different delays, and that leads to a broadening. So this is called scatter broadening. Since these are propagation effects, they are strong functions of frequency. Okay, scattering is nu to the power minus 4, dispersion is nu to the power minus 2. So the strong functions of frequency means that they are best characterized at the lowest frequencies, and GMRT with 300 to 500 can actually give a very high precision measurement for doing this. So that is what we have done. Okay, so this is just basic concept of that. So this is the configuration which we use. We use GMRT as two telescopes. So there are 30 antennas. We divide the 30 antennas into two groups, which we call as subarray. We phase all these antennas to form a single dish, equivalent single dish, which is of the order of 120 to 150 meters. And we put one of the single dish at a higher frequency, which we call as band 5, which is 1260 megahertz to 1460 megahertz, and the other one at a lower frequency, which is 300 to 500 megahertz, and simultaneously observe the radiation from low frequency and high frequency. This 1460 to 1300 gives us a lever arm, and that lever arm gives us the capability to measure the dispersion measure to 1 part in 5. Okay. And some of the dispersion measures which INPTA has measured are unprecedented precision, which we have measured. So we believe that this data would play a very, very important role as far as the overall combined IPTA data is concerned. Okay. So that's just basically some idea about the design of the experiment. And ever since we started the full matured phase of the PTA, we have had several very interesting results. For the first time, we were able to detect a solar disturbance. So sun spews out electron clouds in all directions, and these blobs of plasma are known as coronal mass ejections. Okay. So these are really high density regions of plasma which travel away from the sun in all directions. Sometimes sun sends it away from Earth, sometimes it sends it towards the Earth, and when they reach Earth, they affect Earth's magnetosphere and have a catastrophic effect on power lines, on communications, and so on and so forth. So these CMEs, since they are enhancements of electrons, would also lead to an increase in the dispersion measure. But the increase in dispersion measure is very, very minute, so you need very high precision to measure that. So it has never been measured before, although it has been suggested that pulsars can be used to measure that. In one of our first works, earlier works, as most of you would be aware, Krishna Kumar sort of detected this in the direction of 2145 minus 0750, where we had one outlier point. That outlier point was an excess DM of 0.0005 parsec per centimeter cube. Okay, so it was very tiny, 5 part in 4, but it was an enhancement. And when we compared this with other data like the high energy data and so on, we figured out that this sort of is consistent with a CME which was traveling in that direction and happened to be by luck in the line of sight of the pulsar. So as the CME crossed our line of sight, we saw the enhancement of DM. Okay. So to the best of our knowledge, this is the only detection of a CME using pulsars. We also detected a very interesting profile change in one of the millisecond pulsars, which is 1713 plus 0747. Usually millisecond pulsars are known to show very stable profiles, that is, their profiles don't change. Slow pulsars do, but not millisecond pulsars, and that is one of the reasons why they are used for gravitational wave experiments in the first place. And this happened to be the best, one of the best pulsars, 1713 plus 0747. But we detected a very drastic change, and more importantly, we detected both in high frequency as well as in low frequency. So it opens up new possibilities of looking at this event both from an intrinsic pulsar emission point of view as well as from an interstellar medium propagation point of view. And the work is in progress, and hopefully we will soon publish something more on that at a later point of time. Of course, the other thing which we did was we adopted a technique devised by Tim Penucci for nanograv for higher frequency observation to our low frequency observations. So this wideband technique was applied to 300 to 500 megahertz, and in the words of Tim Penucci, if this works, then you don't really have to focus only on pulsars at high frequency. You can actually do a PTA at low frequency. We are yet not there. We are a little bit far away from that statement becoming a reality, but we thought, why not try it out on GMRT, because GMRT is the best place where we can do that, and Nobel wrote a paper on that. And with all these techniques which we have developed, our first data release, 3.5-year data release, we recently last year we made it public, and now it is part of the IPTA data set also. Okay, so these are just some figures to show all that. Okay, I will not go through these results because probably I am running out of time also, and I will quickly come to where we are right now. So just to sort of highlight this, we all the red circles show the highest precision DM measurements, and again, I think to the best of our knowledge, there is no high precision DM greater than what has been reported here. Okay, although we don't make that claim, but I haven't come across, even after the paper was published, any DM which is better than those red circle marked DMs. So I think the original hope which we had almost basically, as I said, started with a discussion with Dunk in GBT, has materialized in some sense 13 years later in our experiment here. So these are just examples of that. Okay, I will skip all these details. Okay, so why is the in-PTA data important for PTAs? So as I said, we are characterizing the interstellar medium delays which form an important noise process as far as the gravitational wave detection is concerned. Okay, and this is sort of exemplified by this piece of work here by Lentati et al., where they have shown that if you don't account for DM variation or ISM noise, you actually get parameter estimates which have much larger error bars. Okay, so the red points, the red curves there are the parameter estimates. These are all period derivative and things like that. Okay, so the red is the posterior distribution for these parameters when the DM variations are not taken into account. On the other hand, when DM variations are taken into account, you get the blue curves. So you can significantly improve the precision of the pulsar timing array experiment for gravitational wave detection if the low frequency and interstellar medium noise is well characterized, okay, as this simulation shows. And that is precisely what we are doing. That is precisely our contribution to the international pulsar timing array data sets. Okay, probably I will sort of skip this part. Okay, so in the last 6 months what we have done, so let me just sort of come to that. So in the last 6 months, the first thing which we did was we made a public release of our data set. Second thing which we did is somewhere around September we shared this data with the International Pulsar Timing Array Data Combination Working Group, and now it is part of the International Pulsar Timing Array Data Release 3. Okay, and what also we have done simultaneously is we have shared this with European Pulsar Timing Array. As all of you are aware that there is a concerted effort by all the pulsar timing array experiments in the world to have the latest data set analyzed to check for the possibility of a detection of gravitational wave or the stochastic gravitational wave background. Okay, and that is what Maura talked about, I think, last Thursday. And there is a possibility that this data set may lead to a detection. So all the PTAs are working very hard on that, and there are 3 papers which are coming as far as detection or evidence or non-detection, whatever would be the result, which we don't know right now. There are 3 papers coming up. So the INPTA has joined with EPTA to sort of produce one of those 3 P+ papers, and which meant that we have to share our data with EPTA and do joint analysis. So the plots here are showing the data combination both for the IPTA as well as for the EPTA. The left plot is our combination with the EPTA, and the right plot is our combination for the IPTA. Okay, I've just shown one pulsar for illustration. So this is work in progress, and these papers would probably come out around June or by middle of this year. This is likely to come by the end of the year, and that would be our first sort of contribution to the international pulsar timing array experiments. Okay. The other thing which we are doing is we are trying to learn and do our own noise analysis, and Aman, who is sitting here, is spearheading this piece of work where he is actually trying to look at noise models in our own pulsars as well as noise models in our and EPTA combinations. And as you can see in the plot here, combination with INPTA data really sort of improves. In cases of some pulsars, you get a much more tighter posteriors than without including that particular data. Okay, so we hope that for most of the pulsars, the DM variations and the scatter variations which we are providing would lead to tighter constraints on some of these noise models and noise parameters. And again, this is work in progress, and hopefully if as somebody wrote no sleep, if Aman does not sleep, we will in a month's time we will have a paper coming out on this. And the last is the wideband method, which Avinash, Prerna and others are sort of developing. So we have already demonstrated wideband working on the low frequency between 300 to 500 megahertz. What has not been possible is to combine 2 widely separated bands. And in INPTA experiment, we have 2 widely separated bands, 300 to 500, 1260 to 1460. So to apply the wideband method across this entire band is what we set out to do that, and that work is also nearing its completion, and hopefully again no sleep for Avinash, so at the end of that this paper should also come out soon. Okay. The third thing which we discussed again in the morning, and actually this has turned out to be exactly the 3 priorities which we set. Okay, so this I took from some other plot, some other talk. Okay, but it's somehow come out exactly like that. So the third thing is what Tom is doing, and that is at looking at the pulse jitter on this very bright pulsar called 0437 minus 4715. So pulse jitter is basically a wonder of TOAs when you have very high signal to noise ratio, because your pulse profile is not exactly very stable in that case. So you can have some amount of wonder of the TOAs, and this is known as jitter. What the jitter does is it sort of it degrades your data set or degrades your precision. So you need to sort of model for that by using parameters called ECOR and so on and so forth. So again, the hope is that if we are able to characterize the jitter, which you can do best at low frequency, then we can improve the precision. So this is a very preliminary work in that sense. The first jitter measurements, I think Aditya Parsarthi had shown from MeerTime or MeerKAT data, but that was at high frequency. At high frequency, because pulsars have T spectral index, not many pulsars would show jitter. So what we need to do is we need to find out what is the jitter at lower frequency, and that is exactly what Tom, Shin and others in the team have set aside to doing that, and we have some very promising early results. Okay, and hopefully again, if we don't sleep for some time, we will be able to publish this paper also. Okay, so what does the future hold? Okay, so that's almost the end of my presentation. So future holds the new telescopes. Okay, the new telescopes will be order of magnitude more sensitive than our telescopes, and one of them is already there now in the IPTA fold, which is the MeerKAT. And if you actually look at the combination which I showed earlier, okay, Some of the smallest error bar points in that are the meerkat data points. So the reason for that is very simple. The amount of RFI is almost nil. Okay, so you get very high signal to noise ratio profiles, and mean time data is exceedingly clean. Okay, so mean time can actually sort of provide very good data going forwards. But mean time is a time limited experiment for 3 to 4 years. Eventually it will morph into what is known as square kilometer array, which is the next largest telescope which is coming on. Now there are lots of things which we can sort of carry forward from in PTA experiment to an SKA PTA. For one, SKA is also an interferometer, just like GMRT. So like we use multiple beams here, you can use multiple beams as far as SKA is concerned. And right from the day one in the SKA design, 16 pulsar timing beams have been actually put there. So this is some work which Arul and others did, Arul Prabhu and others, to figure out what would be the best configurations if we want to do a PTA experiment, so that we can have a largish sample of pulsars being timed on a very regular basis with a modest allocation of time. Now SK is also going to be like GMRT, that there will be different science proposals, so pulsars may not get 100% of time. So you need to optimize the time in such a way that you are able to cover your entire sample and yet get very high quality data. Okay. So this was some preliminary attempt to sort of do that. Similarly, Maura talked about DSA in her talk. So that is not yet, this is built and may by 2028, 2029 may come. DSA is yet not built, but hopefully will come as a replacement for Arecibo. And again it is an interferometer. Now I don't remember whether Ravi said it will have subarrays or not. Okay, he gave a talk some time back. But if it has subarrays, it can also have a similar kind of a thing there. So again, that would be a fantastic data. And I have not mentioned the third telescope, which is FAST. Okay. And the reason I didn't mention is because sometimes your sensitivity kills you. Okay. So FAST is so sensitive that they don't know what to do. Okay. They have discovered thousands of pulsars, but they can't time them, because you can't time them anywhere else other than FAST. They are so weak otherwise. But for PTA, again, it can give very high signal to noise ratio data. And again, within the international pulsar timing array community, we are hoping that FAST would also contribute its data soon to the entire thing. So the future holds going for this as far as data is concerned. It also holds many other possibilities which are there, particularly in terms of multi-messenger astronomy. But then Gopu is going to talk about it tomorrow. So I will not say much about it, and I'll leave it somewhere here. Okay. So thank you very much for your